It is a pleasure to introduce our first speaker, Dr. Sharad Goel. So Dr. Sharad Goel is a professor of public policy at Harvard Kennedy School, and he recently worked on several problems like policing practices, including statistical tests for discrimination, fair machine learning, including in automated speech recognition and democratic governance, including swing voting, polling errors, voter fraud, and political polarization. So today he will be talking about designing equitable algorithms for criminal justice and beyond. Yes, over to you, Dr. Sharad.
Hi, thanks for that introduction, and thanks for the invitation to join you all today. Can everyone see my screen?
Yes, yes, yeah.
Great. Okay, so today I'll talk a bit about designing equitable algorithms based on experience that my group has had over the last several years, and I'll be focusing a little bit on criminal justice applications, but many of the principles really extend beyond into a variety of applications. So I want to start with this case study of racial disparities in automated speech recognition. So as we all know, we now have powerful speech-to-text systems in our pockets, in our phones. They're widely used as virtual assistants, Siri, Alexa, Google Assistant, for dictation, translation, subtitling, hands-free computing. And these aren't just a nice thing to have. They're really an essential part of life for many folks, especially people with physical disparities. But with many technologies, many emerging technologies, there's worries that they don't perform equally well across for everybody in the population. And so we audited 5 of the leading ASR, automated speech recognition providers, from Amazon, Apple, Google, IBM, and Microsoft by comparing human and machine-generated transcripts for 20 hours of audio of black and white speakers. And so we took all this audio, we had humans transcribe it, and so we knew what the ground truth answers were, what the best transcription was from this audio. We ran all these things through the ASR providers, and then we just compared the error rates from the results that were returned. And what we found was pretty striking. This is a plot of error rates on the vertical axis, and then the different providers on the x-axis. And what we see here is this quite large gap between white speakers and black speakers on these word error rates, so almost a 2x gap across speakers. So even though there's quite a lot of heterogeneity across the quality of these different services, in almost all these cases, we're seeing about a 2x gap in error rates. And so quite a large relative and absolute gap in performance. Now, what's interesting is that even on a subset of identical phrases spoken by the black and white speakers in our data set, error rates were still about twice as large for black speakers. And so this really points to the acoustic models themselves as one of the sources of creating these disparities. So if you know a little bit about how these automated speech recognition models work, there are really 2 components. There's the acoustic model, and then there's the language model that's looking at grammar. And we're really seeing, what we're finding is that these language models perform comparably, but it's the acoustic models that are really creating these disparities. So even when the exact same phrases are spoken by black and white speakers, we're seeing about this 2x gap in errors with worse performance for black speakers. So what do you do with this type of finding? I think there are a variety of immediate interventions. I mean, the first and arguably the most obvious is to collect more training data, more diverse training data, both of what's called AV speech, African American Vernacular English. This is a term that linguists often use to describe the variety of English that many black speakers use in the United States. but also a variety of other styles of English. And one of the reasons I got started on this project is that for many years, when my relatives, my parents, would leave messages for me on the phone, and these would get automatically transcribed, they really came out as being nonsensical, and the speech recognition services really weren't appropriate for people who weren't speaking what's quote unquote standard English. So it points to this value of collecting more diverse training data. The second is simply to invest more resources broadly into ASR systems, and including the institutions that build them, to ensure that that these ecosystems are more inclusive. So you can imagine that if we had greater representation among the types of people who are building and using these systems, then these types of disparities would be more quickly recognized, and arguably these products would be improved before they were actually released into the wild. The third is assessing and regularly reporting on progress over time. We were able to do this work, but it was a fair amount of logistical challenges that we encountered, and it was certainly difficult for us to do this from the outside. And so having this type of internal auditing, regular reporting would be quite useful. And then finally, learning from the types of legislative progress that have been made in other domains, for example, computer vision, where we might have more oversight and higher standards for deploying these types of technologies into the wild. So if you want to read more about this particular example, please check out our paper that we released last year, that we published last year in PNAS. So now, with this example in mind, I want to talk more broadly about the dominant ways of understanding fairness, particularly in the machine learning and computer science community. And what I'll offer is a critique of what I call deontological approaches to fairness. I'll define this term deontological in a minute. But this is one way that I think of many of the approaches that are now becoming popularized in the computer science community. And in response to these deontological approaches, afterward, I will present an alternative consequentialist approach to fairness, which I think can help us mitigate some of the limitations of this dominant approach. Okay, so in much of the material that I'll talk about in this part of the presentation is drawn from this paper with Sam Corbett-Davies, The Measure and Mismeasure of Fairness. So, as many of you likely know, many high-stakes decisions are made by first estimating either statistically or just intuitively estimating the likelihood of some adverse outcome based on the available information. So in lending, we might estimate the risk of default using credit scores. Incarceration, in many cases, is based on the risk of recidivism, the risk of future offense. And the idea is that decisions that are guided by statistical risk assessments, in theory, can be more equitable, they can be more consistent than those made by intuition and expertise alone. But at the same time, there's a lot of worry that these types of tools can embed bias themselves. So even though there's this potential benefit of limiting bias from unaided human decisions, there's a real concern that bias itself will creep in to these decisions by automating them. Now, what do I mean by deontological ethics? So here, this is this idea, not only in the algorithmic world, but kind of much more broadly. It's this idea that the morality of an action is judged based on whether that action itself is inherently right or wrong under some normative set of rules, rather than the consequences that stem from that action. So I might say that this, I'll give you many examples of this in a minute, but I can say that there's a certain way of doing things. There's a process by which we do something. These are the rules that I'm laying out, and if we deviate from those rules, then that itself makes that action inherently wrong, even if the outcome, the consequences of that action in some sense are legitimate, the way that I did that, or the reason I'm doing this itself could be deemed morally wrong. So this is what I mean by deontological ethics, and I'm going to connect that idea to this algorithmic framework. Okay, so one of the dominant approaches to the dominant mathematical approaches to fairness is what I call classification parity. And so here the idea is that an algorithm is considered to be fair if error rates are approximately equal across demographic groups. And for simplicity, I'm gonna take this kind of somewhat reductionist, this simplistic view of talking about two race groups, white and black individuals, in particular race groups that are salient to the United States. And again, the idea here is that an algorithm is considered fair. The rule is that the algorithm is fair if error rates are approximately equal across these groups. And again, this makes a lot of sense. And we saw in this motivating example that I started with automated speech recognition, that here we saw these big gaps in error rates across groups, and that I think to many people feels like it's inherently problematic. And so this is part of where this intuition is coming from when we're demanding this classification parity. So this isn't only something that has been adopted in the computer science community. It's really something that has gained traction in public policy circles as well. And so this is some legislation that was proposed in the United States a couple years ago in the context of what's called pretrial risk assessment. So after someone is arrested in the United States, a judge has to make this high stakes decision about whether or not to detain or release that individual pending further court proceedings. And so this is what's called a pretrial risk assessment. The person hasn't been put on trial yet, but is pretrial, and there's this decision made about whether or not this individual is sufficiently safe to be released into the community. And so this legislation was designed to ensure that these risk assessments, these algorithmic risk assessments, were indeed equitable, were fair. And this is the language that I'm going to read from now from that proposed legislation. Pretrial risk assessment algorithms shall not be used by the state until first shown to be free of bias, meaning that an algorithm has been formally tested and the rate of error is balanced as between protected classes and those not in protected classes. So again, this very, very simple, intuitive idea that fairness, the rule for fairness, is that the error rate is balanced or approximately equal across groups. It's a very simple idea. Now, what I'm going to argue is that even though this idea, this deontological idea, this rule for fairness makes a lot of sense, or it feels like it makes a lot of sense, in fact, it's there's quite a bit of subtlety in this idea. Okay, so what do we mean by error rate? There are many, many ways of formalizing error rates. I'm going to take one particularly common approach, and this is what's called a false positive rate. And to be super concrete, I'm going to phrase the definition of the false positive rate in terms of this pretrial risk assessment application. So what does it mean here? It means among people who ultimately did not go on to reoffend. Remember, the risk assessment is designed to help us identify those who do go on to reoffend, their risk of recidivating, their risk of reoffending. So here the false positive rate says among people who do not ultimately go on to reoffend, what proportion were deemed high risk by the algorithm. So these were false positives. Even though they were not positives in reality, they did not go on to reoffend, they were tagged as positives falsely by the algorithm. So this is our false positive rate. Okay, so now a study in the United States a few years ago looked at the use of one particularly popular algorithm for these pretrial risk assessments, and looked at the different error rates that this algorithm was leading to in two different populations of Black individuals and white individuals in Broward County, specific jurisdiction in the United States. And what they found was pretty striking. They found that among Black defendants who did not go on to reoffend, about a third, 31%, were deemed high risk by the algorithm. And among white defendants who did not go on to reoffend, about 15% were deemed high risk by the algorithm. So this is a pretty big gap. It was a gap of, of 15 percentage points, so in absolute terms, about a 2x gap in relative terms. So quite a big gap, both in absolute and in relative terms, since this is the gap, again, in the false positive rates. And again, you look at this and you're like, intuitively, this feels really bad. It feels like something has gone fundamentally wrong in that, maybe somebody messed up when they were designing this algorithm. And that was the first thought that I had too when I saw this example. I was like, oh, okay, well, clearly we can do better, that we need to work harder, and we can design a more equitable algorithm. And now what I'm going to argue again is, in fact, there's something more subtle happening here, in that this gap in error rates doesn't necessarily mean what we first think it means. So I'm going to do this in pictures. So we imagine we have these two groups. We have the blue group and we have the orange group. And there are a couple of features of this diagram that I want to point out. So the first is that underneath each of these stick figures, I have these numbers corresponding to the estimated risk of recidivism, the risk of reoffending. So I have these low risk individuals here on the left, so 10, 20% chance of reoffending. These high risk people on the right, 50, 70%, 80, 90% chance of reoffending. I'm going to assume that, in fact, all of these risks are perfect estimates of risk given the available information. So there's no statistical estimation error in these things. We're just going to assume that all this is perfect. I'm going to still demonstrate that there's some kind of subtle issues here that cause us to more carefully try to understand what these error rates mean. So in the absence of statistical error, we still have these very complicated questions of interpreting error rates. So we have these error rates for each individual. Because we have these two different groups, anytime I split my population into groups that are non-random, I can expect there to be distributional differences. And so here what we see is this orange group is higher risk than this blue group. This isn't saying anything inherent. It isn't saying that the blue group is inherently less risky than the orange group, but really this might be a product of different covariate distributions in these different groups, and that is what's driving this different observed distributions of risk. So I have these different distributions of risk in these two groups. And now finally, I have this line that I've drawn here that separates what I'm going to call the quote-unquote high-risk individuals from the low-risk individuals. So we have these. So I have to partition. If I'm going to make a binary classification of saying high risk and low risk, I have to pick some threshold for making that classification. And here I've somewhat arbitrarily just picked 50%, but I could draw this anywhere. But here I've drawn it at 50%. And I'm going to call these people high risk and these people low risk. And importantly, I'm drawing a single threshold. So I'm making this decision on whether or not someone is categorized as high risk or low risk only based on their risk itself, not based on group membership. And so I'm applying the exact same standard to everybody. And arguably, this is an equitable way to classify folks. If I give you their risk, and I say these are perfect estimates of risk given the available information, now I'm going to classify you only based on that risk score. Arguably, that is one kind of intuitively fair, equitable way of making that classification. So now let's see what happens when I dive into this example. Let's look at this blue group. Now remember, what is my definition of false positive rate? Among people who do not go on to reoffend, the proportion that are deemed high risk. So now I'm highlighting these people that kind of randomly went on to reoffend. So 5 people randomly went on to reoffend. That means 8 people in this simple example did not go on to reoffend. Those are the ones marked in blue. Of those 8 people who did not go on to reoffend, 2 of them are to the right of this dashed line, and those are the people who are deemed high risk. And so in this case, I just have 2 over 8, or 25% false positive rate. And so about a quarter false positive rate in this example. So now, just mechanically, I'm going to look at this orange group. So orange group, remember, is a higher risk group. The distribution of risk is shifted to the right in this example. So now I have, this is a higher risk group. On average, more people will reoffend. That means that fewer people will not reoffend. That means that the denominator of this on this example will be smaller. And now the way that I have drawn this picture, among those people who do not go on to reoffend, a higher proportion will be deemed high risk. And so here I have this 42% false positive rate. And so again, this is just kind of mechanical. I have these two different distributions of risk, this lower risk group in blue, this higher risk group in orange. And in large part, because of this different distribution of risk in these two different groups, I have these differences in false positive rates. And so here, even though I apply the exact same standard, I have this difference in false positive rates. So now, again, that was just kind of a stylized example showing how these differences in false positive rates can arise even when we arguably are making an equitable classification decision based on the available information. Now let's look at the real data. In the real data, we don't know exactly what everyone's risk is. That's not something that we can easily, or that's not something we can definitively answer. But what we can do is estimate the risk based on the observed information. And so here again, these are estimates of the risk distribution across these two different groups. So this corresponds to the stylized example that I was talking about. And what we see here is that this red group, in fact, it does have a very different risk distribution and a heavier base rate, higher base rate, a heavier tail than the blue group. And what this example, this stylized example shows is that when I have these differences in base rates, when I have these differences in risk distributions, I can generically expect to have differences in error rates themselves. And so this example is highlighting this idea that differences in error rates are what we expect when we have differences in risk distributions, and in many cases we expect differences in risk distributions. Okay, so this phenomenon is related to what economists called infra-marginal statistics. And so what is this idea? This means that a statistic is infra-marginal if it depends, and here what I mean by statistic is something like a false positive rate. Every kind of summary statistic of error that we can think of is infra-marginal in the sense that I'll describe now, in that the statistic depends not only on our threshold for classifying people as high risk or low risk, but it also depends on the distribution of risk. So even though we have this normative idea of risk depending on applying the same standard to everybody based on that risk score, these infra-marginal statistics like false positive rates and like really any other error rate statistic that we can think of doesn't just capture what's happening at the margin, at the threshold. It really depends on what's going on with the entire distribution. And so now you might think at this point, okay, I understand mechanically when I have differences in risk distributions, then things will just be different. I expect to see different error rates. But why? But that is itself problematic. It's even though I have these, just because I expect to have differences in error rates doesn't mean I should be happy with these differences in error rates. And it still might mean that these groups with higher error rates are being disadvantaged in some sense. So now what I'm going to show is a very simple example that even pushes back against that quite reasonable intuition. So remember, here's my orange group, this higher risk group, and this was the 42% false positive rate group. And now, how can I lower the risk in this group, there's false positive rate in this group? Well, I can go out and arrest a bunch of college protesters. So of course I'm being facetious here. We're not going to actually go out and arrest a bunch of college protesters, but the point here is if I were to do this, what's going to happen? The algorithm correctly identifies that these college protesters are in fact low risk. It classifies them as low risk. Now, most of those low risk individuals are going to end up in the denominator. And now all of a sudden I have this relatively low false positive rate. So I went from this situation where, oops, I went from this situation where I'm seeing this high false positive rate in the orange group relative to the blue group, and might say, okay, well, I'm burdening this orange group with this high false positive rate, to this situation where my false positive rates are equal, my error rates are equal, but clearly I've made the orange group worse off by doing this. I burden that orange group more, even though if I just looked at these summary statistics, I would say, oh, things are actually not so bad now between these two groups. So the point, again, isn't that I'm worried about incentives. I'm not worried that if I say design my algorithm to equalize false positive rates, I'm going to encourage people to go out and make this orange group worse off. But the point here is that if you don't consider the distribution of risk, it's very hard to interpret what these error rates really mean. Now, what is the difference here? I mean, we in the machine learning community, we use these error rates all the time. This is kind of the bread and butter of evaluating and developing new approaches. And so is this how does this discussion that we've been having, how does this relate to our kind of normal state of affairs? Now, here, what I'm arguing is that in traditional machine learning settings, in the settings where we're familiar, what is our usual mode of operation? We compare multiple models on the same data set. And so we say, here are my 5 benchmark state-of-the-art models. I'm going to introduce a new model. I'm going to take some test data set. I'm going to run all my models on that test data set and see which performs the best. That's sort of our standard machine learning pipeline. But this approach, this fair machine learning approach that I just discussed, here the idea is effectively we have one model, one risk assessment tool, but we're evaluating it on multiple data sets. And so here we took our one model and we said, let's look at the performance of that one model on 2 different subpopulations in my larger population. And now let's compare error rates on those 2 subpopulations. So that is a pretty difficult thing to compare. So this is really an apples to oranges comparison relative to what we're normally used to in machine learning, where we're saying we have multiple models that we're comparing, but on the same data set. So it's similar, but very different in a way that makes it hard to interpret the results. Now, in some settings, these differences in error rates across groups can actually be a strong indicator of algorithmic problems. And so going back to this automated speech recognition example that we started with, unlike pretrial risk assessments, we have pretty strong reason to believe that with more data, with possibly better models, there shouldn't be a difference in error rates across different types of speech that we encounter. So it's not that the type of English that's spoken commonly by white Americans is different than the type of English that's commonly spoken by Black Americans. There's nothing kind of inherently more difficult for automated speech recognition to transcribe speech from these 2 different subpopulations, and so we would expect the error rates to be comparable, which is very different from the situation that we have in many of these risk assessment algorithms, where there we generically do expect base rates to be different. And when you expect when base rates are different, that suggests that the difficulty of the problem, the statistical difficulty of the problem, is in fact is quite a bit different as well. And so there we expect differences in performance, differences in error rates. Okay, so this was just a sort of brief critique of the style of reasoning, this deontological mode of reasoning that has become popular in the machine learning community, where we say what our rules are, for example, demanding parity in error rates, and then we evaluate our algorithms relative to those rules. So, I've tried to argue that things can go quite wrong when we take that approach. And so now I want to present an alternative, what I call a consequentialist approach to fairness. And so here I want to give a slightly different motivating example. So in many jurisdictions, especially in the United States, people can be jailed for failing to appear in mandatory court appointments. And so as a result, it's possible to reduce this type of incarceration by helping people appear in court. And so one way to do this is to provide folks with free door-to-door rideshare service. So one of the big barriers to getting to court is transportation. So people don't always live close to the courthouse. There's not necessarily good public transportation, and they're not easy ways to make it to court. And so one alternative, or one possibility to support this type of court appearance, is providing people with rides to get to court. Now, of course, it would be better to just not jail people for these types of, I would say, minor infractions, but that's harder from a policy perspective. And so really I'm gonna focus on this question of how do you equitably provide this type of rideshare service to folks who have upcoming court dates. So imagine we have some pool of money, $100,000, to purchase rides for people with upcoming court dates. And the question is, who should we give rides to? So this is actually, it's not a hypothetical. We're preparing to give out rides next year in California, and we're up against this problem of how do we decide who to give these rides to? So one pretty natural approach to this problem is to simply allocate the rides in a way that maximizes the number of people who make it to court. And so conceptually, this is straightforward. Statistically, it's hard, but conceptually, it's pretty straightforward. We estimate the heterogeneous treatment effect. And so we say, how likely is it what is the extra boost, the extra chance that someone is going to go to court if I give them a ride? I can estimate that maybe through a randomized controlled experiment, but there's some way I can estimate that. And now I just rank people and allocate by the estimated effect per dollar. So some people live further from the courthouse, and so it might cost me more to provide that ride, but they might also have a large effect. And so I just look at what's that boost I can get by giving them a ride, divided by the cost of providing that ride. Now I have an effect per dollar, and I can just rank people by this estimated effect per dollar, and then allocate from the top of the list down until I run out of my budget. So this is a very natural approach to maximize the number of people who make it to court. Okay, so now what can go wrong? So here's a picture of a particular county in California where we're planning to roll out this service, and these dots here represent the demographic of the individuals by their race. And what we see in this particular county, and this is very kind of broadly similar to what we see in many parts of the United States, is a lot of segregation. And so we see that the colors represent that demographic group defined by race or ethnicity, and what we see is a lot of segregation. And in particular, what we see is that the people who are going to be most expensive for providing these rides for getting to the courthouse tend to be of Asian descent. They live on the outskirts of the city. The courthouse is right around here. The outskirts of the county is here, and these folks are going to be much more expensive to provide rides to than the people who are a bit closer to the courthouse, which are a different demographic than the people who live on the outer edges of the county. And so if we were to take this this optimization approach, then we're likely to disadvantage this non-representative set of people who live out on the fringes of the county. Okay, so this introduces this tension. And there are a couple ways that we can deal with this tension. So the first is this deontological approach that I started out the talk with, where we might demand an equal proportion of people receive rides in groups defined by race or other characteristics. That's one approach that we can take. And if we do that, we have this trade-off. So here, these are hypothetical numbers, but I think they hopefully make the point that we might say, well, first we can just optimize. We can forget about all of these equity considerations. We can optimize for the most number of people getting to court, and we might have something like 1,000 new appearances, and 30% of one group gets rides, and 20% of another group gets rides. And so we have this disparity in who's getting the rides, but we get the most number of people to court. Now, an alternative is, say, if we demand equal allocation, we might get 800 new appearances, so fewer new appearances, but 20% of people in each group gets a ride. So we're able to balance the number of people or the proportion of people from each group that gets a ride, but we have fewer. The cost of that balancing is that a fewer number of overall people will make it to court overall, and so we have this tension. And so this traditional deontological approach, this rule that says I need to have the same number of people make it, or the same proportion of people make it to court from each of these groups, ignores the outcomes, the consequences of that mode of reasoning, of that type of policy decision. And so in general, we can expect, if we're ignoring the consequences, then the algorithms that we develop are going to be misaligned with our true preferences are as policymakers. And so here, this approach, this consequentialist approach, is to aim for decisions that maximize stakeholder utility, including one's preferences per parity, but are really directly optimizing for the outcomes that we care about, rather than laying out these rules ahead of time and then hoping for the best. So again, let me just sort of, I can simplistically think that we have this spectrum of, on one side optimizing for appearances, on the other side optimizing for equal allocation across groups, and my real preferences might lie somewhere in the middle. And so now this introduces this trade-off. Here I can say the number of additional people that appears on one axis, the percent of people in some target group that receives transportation benefits is on the other axis. All of these points are points that are feasible given my budget. I can say, okay, I can create policies of handing out my budget in ways that gets me to any of these points in this gray area. And so I can realize this point in red. If you want this point, I can give you this point. In reality, you wouldn't want this point. You would rather be on this frontier here. And so this is the Pareto frontier that's being sketched out. It says this point dominates this point, so I get more people with still maintaining the proportion of people in the target group who receive benefits. I can still get more people overall by selecting this point. These points here, I might want them, but they're out of budget, so I'm really restricted to points that lie on this curve. And so now I can say, well, which of these points on this curve should I pick? One option is that I just maximize for appearances. This, again, this straightforward, naive optimization approach of saying, let's forget about equity considerations, let's maximize for appearances. Another approach is, again, this deontological approach of, let's say, I just want demographic parity, and so this is going to place me somewhere else on this curve. Ahead of time, I won't know where I'm going to fall on this curve. If I just say my rule is demographic parity, I won't know where I'm going to lie, but I'll lie somewhere on that curve. But then really what I might care about is maximizing my utility. And so here, again, the idea is I want to balance, I want to explicitly balance this trade-off, that my desire to maximize the number of people that make it to court, and also ensure that these are equitable. And so here I might choose a point that's somewhere in between. And this idea of this consequentialist approach to fairness is simply saying, let's be explicit about the trade-offs and then select that point with these trade-offs in mind, rather than putting the rules first and then hoping for the best. Okay, so summarizing here, that this deontological approach, we force our decisions to satisfy particular mathematical fairness constraints, for example, demographic parity. It can and typically will result in suboptimal outcomes if we're not cognizant of the downstream consequences of those types of constraints. So here, very quickly, in reality, so I sketched this general idea of how we might think about designing fair algorithms. In reality, we have to learn these policies from data. I'm not going to go in that now, but I'll say that this is a variant in practice. What we're doing here is a variant of contextual bandit algorithms. And if you're interested in reading more about that, you can check out our paper on learning to be fair. So just in the interest of time, I'm going to skip this last part, and I want to wrap up by summarizing. So many popular algorithms, for example, automated speech recognition, exhibit troubling disparities. Past attempts to address these inequities have focused on these deontological approaches, these rules for requiring error rate parity, like requiring error rate parity, but they can exacerbate problems if we're not careful. And so an alternative is this consequentialist approach to directly consider the trade-offs that are inherent to policy decisions. So thanks everybody for listening to this presentation. I'm happy to take questions.
Thanks, Sarath. So yeah, we have one question from the audience, but I will first of all request if there are any questions from the panelists.
Hi, Sharad. Animesh here. So
Hi.
it was a great talk. So I was more keen on the first part of the talk that you described about the discrepancies and the disparities in the speech recognition systems. So that was kind of interesting. Like it reminded me of the gender shades paper. So where they were looking into image recognitions and cafe recognition and face recognition softwares. So recently, like what we kind of saw is that if you have adversarial attacks to these kind of images, actually the disparities are even larger. So I was wondering, like, since ASR systems are typically noisy, so, and if they're like made to work in, say, some supermarkets, malls, so noise is kind of inevitable. So do you think that in a similar way as we have seen, so this work is going to come up in ICWSM 22, will this disparity be more pronounced? Like, what would be your take on that?
Yeah, I mean, I think it's definitely possible. I mean, and also to make this connection, I'm glad you brought up this gender shapes work. That was definitely one of the inspirations for the work that we were doing here, in one of the most prominent examples of these disparities in performance across these types of models. And so I haven't looked at the performance of these in these noisy environments, but I think it's very possible that the disparities become even more pronounced in less than ideal settings.
Thank you.
Yeah, thanks, Professor Animesh. Yes, so we have one question from Aman, and the question is this: that in the illustrative example for the pre-trial risk assessment, why is FPR a useful metric to look at and not something like precision, given the likely imbalance between the high and the low risk individuals? And does the analysis gets affected by this choice?
Oh yeah, so precision. So yeah, it's a good question. So in fact, the argument that I presented applies more or less unchanged for everything you can compute from a confusion matrix. So including precision, recall, true positive rate, false positive rate, even AUC, all of these metrics of error, they all apply this idea of infra-marginality. It applies equally to all of these different measures.
Okay. Yeah, thanks, sir. Yeah, one more question. So there are three questions by Ajay. Maybe I will ask them one by one. So the first question is: history of group decide the future of the group. How fair it is?
Maybe I'm not quite sure I followed the.
Exactly. Yeah. So even I'm not very sure about this. So maybe we can then move to the next one. One or multiple models. What model is trained on biased data, and do we expect fairness? Not very sure about this either. For ASR overlap speech, more than two speakers are talking at same time. How to address this, and few or many good data sets you point to?
Yeah, so I mean, for this last thing, I think we, again, in this situation of less than ideal settings, when these are harder transcription tasks, I think it's quite plausible that we see differences, even larger disparities in error rates. And so, we're already seeing these 2x gaps in error rates, and we can go to these natural, even more real world settings, then we might expect to see these gaps to become even larger.
Okay. So that's all questions that we have from our side. Yeah, thanks, Sharad, and thanks for accepting our invite. Thank you.
Thanks. Yeah, thanks for the invitation, and I'm really happy to participate in this.
Yeah, thank you very much.